we've had enough of solution aqueous chemistry, so let's talk about how periodicity plays into the electronic properties of solids at a somewhat basic level. So we'll kind of frame this in the discussion of the context of conductivity in solids. So we'll talk about mostly about crystalline solids, so where everything is repeating. So the basic idea for conductivity is if we have our the nuclei of your atoms fixed, so I'll kind of put positive charges everywhere. So here are my atoms. They're positively charged if the electrons are gone. Okay, so we're in a repeating thing. Here are my atoms. And then our electrons are associated with each nucleus of every atom. And then so if the electrons can move around and hop between our different atoms, then our material will be conductive, right? So put minus charges. So everything is neutral to begin with. So how mobile these can move around is what makes things conductive. And then there's a so-called sea of electrons model for metals. So you can think of them as sloshing around. But what governs that? And we could bring this back to MO theory. So let's think about, let's say, a lithium atom. So here's my lithium. OK, so it has a 2s electron. And then so this is, of course, in the s orbital. So when we start thinking about bonding, we could, here's my 2s orbital. We have dilithium. And then so we could form an MO diagram, easy peasy. Sigma, sigma star. So one electron here. So we'll then have paired, it's bonding, anti-bonding. Dilithium is also apparently the fuel for faster than light warp drive in Star Trek. But yeah, so then so here's just two. But if we want to make an extended solid, we need to add more. So if we add, let's say, a third lithium, then we have another s orbital coming in. We form bonding, anti-bonding combinations. Here are my 3 linear combinations, our MOs. So we could have, let's see, all in phase, all out of phase, and then maybe one in between, something like that. OK. And then we have 3 electrons. So 1, 2, 3. So this goes on and on and on until if we have like a giant chain of it, then we'll have many different, so for every, let's see, so if we want like maybe like a mole, 6.022 exponential to the 23, a mole of lithium atoms, we're going to have like Avogadro's number of MOs. So it's going to form, and they're all going to kind of stack together, so you're going to form like a bunch of little lines. They're all together. It's going to spread out. Some of them are filled, some of them are empty. So what we typically draw it is as sort of a band diagram. So this band is just a representation. It's a rectangle that represents all of these, like Avogadro's number of MO energy levels. And so at the very bottom, if we're in a row, it's going to be the all-in phase combination. And then at the very top is going to be the all-out-of-phase anti-bonding combination, et cetera, et cetera. And because the s orbitals of the lithium atom are half filled, this band will be half filled with electrons. OK. And then so this is kind of the representation of the electronic structure of lithium metal. So the reason lithium metal is a metal is because this band is half filled. So then these electrons are not stuck. So these electrons can easily go into empty, delocalized orbitals. And then so you could just easily kind of excite to these empty orbitals and then delocalize. And then as a result, they can move around very readily. So this is conductive. Conductive metal. OK, so this is lithium metal. OK, so then you might wonder then, magnesium, on the other hand, let's say magnesium is 2s2. So in principle, this is fully filled. So if we did that same procedure, our S band should be completely filled. So this is the band from the 2s. And then if these orbitals are all filled, then it shouldn't conduct because electrons are all stuck. There's no empty orbital for them to hop to, so they shouldn't be able to move. But the key part here is that magnesium is actually, here's our kind of 2p, and then we have our 2s. So 2p's, because we can form, let's say, we could form this bonding combination. So these bond very well because they're excited toward each other. So then the p band, so this p orbital energy is going to kind of expand out into an empty band, while this s combination is going to expand out into this filled band, which I'll draw kind of in pink. So they'll overlap, which means that it's very easy for these s electrons to go into these empty band of p orbitals, and then so this is still, magnesium is still a metal and conductive. So this is generally what happens. When we have orbitals that can bond together, the more bonding they have, the bigger the spread is. The bigger the distance between the bonding and anti-bonding orbitals because of the greater orbital overlap. So the p band spreads out more than the s band, and as a result, they overlap. And then the key part is that the electrons have to be easily accessing these empty orbitals to be conductive and delocalize across your entire solid. OK, so now that we know generally what happens when we form this extended structure, let's discuss kind of the different types you're going to end up with. Sorry, bear with the erasing. OK, so we just talked about whether something could be a conductive metal. So again, that's if you have maybe a partially filled band or a filled band overlapping with the empty band. So again, you have to easily access these empty delocalized orbitals. We could have an insulator. So an insulator is a scenario where you have, let's say, your filled band. So all your orbitals over here are filled with electrons. And then you might have another band up here that's empty. So these are from your empty atomic orbitals that are then bonding. But because this gap is very big, this is called the band gap. It's not easy for these electrons from these filled orbitals that can't move to access these empty orbitals, so as a result, you have insulators. And then in the middle, we have maybe situations where you still have a filled band, and then this band gap, it might be smaller and may be accessible with heat or light. Oh, and terminology-wise, this is called the valence band, because that's where your valence electrons are, and this is the connection band, because that's where the electrons have to be if you want to conduct. So this is the semiconductor. OK, so these are the kind of situations. So this, again, follows your periodicity trends. If you're very low electronegativity, let's say, kind of as general guidelines, but don't take too much into them. So this is chi less than 1.9, it's metal. And then here is if we have 1.9. And then here is if we have chi greater than 2.2. So of course, as we go very far to the right, carbon is an insulator unless you have a certain packing structure like graphene. As we go further down, we might have silicon as a semiconductor, something like that. And then far left, we had our examples of lithium, sodium, and if we're staying in group 4, like lead, for example. So what determines, so these are for the pure elements of whether the pure element as a solid is going to be a metal or insulator. And then this, of course, also changes a little bit for binary compounds. Let's say the oxides will also determines on some periodicity properties. So the key part for electronegativity is this changes it, and then but also between semiconductor and insulator, what governs that is also you think about silicon versus carbon electronegativity, but also kind of strength in bonding. So the stronger you bond with each other, then the bigger splitting you have between the bands. So as we go further down the group, then from carbon through silicon to germanium to tin to lead, the bonding gets weaker. And then so as we get weaker and weaker, then we're going to get smaller and smaller band gap. And then that's why as you go all the way to lead, you might become a metal because this distance gets smaller and smaller. So things to consider: electronegativity, and then how strongly you bond your compounds.